Futura Bridge truly is a fascinating project. A fully FRP bridge solution that tackles and disrupts traditional design thinking. It tackles the challenges set by the UK government's Access for All programme and contributes to the sustainability goals of the UK transportation sector. The partners in the Futura Bridge project are Covey, Marks Barfield Architects, Network Rail and the National Composite Centre. And the collaboration environment that runs throughout the project team has been absolutely first class. This presentation is divided into two sections. I'll start with a very brief introduction to the project and some scene setting. I'll then go on to describe the FRP bridge itself and introduce some of the key design challenges that we're faced with. I'll then finish off by offering some commentary on how I see this type of solution becoming a key player in the future of footbridge designs. I'll then hand you over to Kaloyana of the National Composite Centre, who will describe some of the challenges associated with the manufacture of a bridge of this kind. So to kick off, I'll give some context to the project, which originated from an entry to the Network Rail Design Ideas competition run by REBA in 2018. The remit of the competition was to reimagine the future of station footbridges across the UK railway network. Part of our competition entry is seen on this slide and on the previous one. It's fair to say that FRP is not a new material. It's used extensively in other industries and for many different applications. If you own a modern car or take modern public transport, the odds are you've come into contact with this material. Our concept takes some of these high-end innovations, particularly in the aerospace and the automotive industries, and adapts them for the civil structural space. The bridge is a fully FRP shell structure, making use of the incredible strength-to-weight ratio and the enhanced durability characteristics of this fascinating material. The shape and form of the bridge is respectful of the existing 19th and 20th century architecture on the network and brings this into the 21st century, adding lifts to improve access and resembling modern construction techniques. In the months following the competition, it was clear that Network Rail were keen to progress this solution to add to their growing catalogue of generic footbridges, which I'm sure many of you will have seen some of. In order to provide a platform to bridge the gap between a mature material used extensively in one industry and introduce this material into another, it was decided to design and build a 1-to-1 scale prototype that could undergo rigorous testing at every stage of the process, from design challenges all the way through to the material and manufacture stages, and finally physical and aesthetic testing. Although the project is focused on a prototype of a single bridge span, orientation and configuration, the design team are of course developing parallel solutions for multi-span options as well as many other configurations such as Z shapes, differing platform heights and span lengths, and the option of a roof. The goal is to generate a catalogue of Futura bridge solutions that can be adapted to any platform configuration. The project is currently midway through the detailed design stage, and the prototype is due for completion early next year. Now, it's not often you have the opportunity to build and test a bridge at a 1-to-1 scale as an R&D piece and facilitate a platform to allow the design process to organically evolve and feed the ongoing lessons learned back into the design loop. And I can say that as a structural engineer, this has been and continues to be a truly rewarding way to work. The main purpose of the project is of course to test the use of FRP material in this application. I'm the first to admit that we've not solved every problem and there still remains many challenges in the project. But the learning curve is steep and we're getting closer and closer to a solution that we believe will positively disrupt the market. Having set the scene, with the time I have, I'll discuss this design in a little more detail. The bridge is a fully integral FRP monocoque shell structure, with all of the structural loads being transferred through the FRP skin. The prototype bridge is supported on simple rectangular shallow foundations, and of course could consist of traditional or screw piles or other foundation types if site conditions necessitate it. The bridge acts as a rather complex portal frame, but a portal frame nonetheless. This image shows a cross-section at midspan. The lightweight FRP shell consists of a series of internal closed cells, which are used to stiffen the box and distribute local and global loads to the foundations. The space between the cells is occupied by high-density foam to act as a permanent formwork inside the box to support the fibers during the infusion process. This gives incredible design freedom, with the foam blocks being trimmed using an industrial robot. The parapets are connected to rigid points on the upstand and transfer loads into the box at diaphragm locations. The highly complex geometry is driven by a set of parametric scripts, linking the likes of Grasshopper, Rhino, and our structural analysis software LUSAS, as well as feeding information to the National Composite Centre's fabrication models. As you might have guessed, the parametric nature of the geometry means that through a series of inputs, the geometry can be updated instantaneously, and the design loop carried out at a fraction of the manual time. This is particularly effective when designing with FRP, as it comes at no additional cost to tailor the thicknesses and the fiber orientations of this extremely anisotropic material. This gives rise to extreme material efficiency and a lean but elegant design. An interesting, or perhaps even novel, method of FE analysis was also developed on the project, whereby the structural model and mesh characteristics are controlled through Grasshopper itself, maximizing the flexibility that it offers. The construction sequence involves installing a set of 7 modular elements. These lightweight elements arrive to site and are installed during a nighttime possession of the railway using a modest mobile crane. Factory connections are bonded and site connections are bolted, minimizing the time required for the crane to be in operation. The detailing in the site joints has received extensive design effort to enable an optimized installation procedure. Other features of the bridge, such as the glass balustrades, the lift towers, the drainage, and the lighting, have all been integrated into the design of the FRP shell. I'm going to play a short video of the scheme while I move on to the final part of my presentation regarding sustainability. The truth is, this bridge form has very high sustainability potential. But, and there is a but, it may not be as clear-cut as its reputation might give it credit for, and this topic needs careful consideration. I wanted to briefly pass comment on how I see this material being used effectively in the bridge industry in the future. There's no debating the strength-to-weight ratio of the material. It's well documented that it performs significantly better than any other mass-produced structural material used in the industry. On top of that, the structural performance can be optimized through an additive manufacturing process by altering thicknesses more regularly and orientating fibers only where they are needed. This offers the potential for lightweight structures in many different forms. And due to its almost inert material characterization, it doesn't corrode, meaning you should not have to perform large-scale maintenance rehabilitations every 20 to 25 years like you might with competing materials. However, where it falls down is in the cradle-to-gate characteristics of the inherent material. Dry fiber and resin are not necessarily the best materials for the planet, so careful material choices are needed to balance the whole life sustainability benefits of FRP structures. There are many biomaterial alternatives that are receiving extensive ongoing research at present, giving their sustainability potential. Furthermore, although material recycling is possible with FRP, at present the technology is by no means mature, nor scaled. And so I believe more work in this area is needed. Through the Futura project, we are taking full advantage of the sustainability benefits of this material and doing our bit to advance and promote the areas that we feel need improvement, as I personally feel this material will be a strong player in the future of bridge construction. I'll now pass you over to Kaloyana.
Thank you, Finn. Today I'll be presenting on behalf of my colleagues at the National Composite Center who are involved in the Futura Bridge project. For those of you who don't know, NCE is one of the 7 high-value manufacturing catapult centers across the UK, which provide innovation support for businesses. The center was opened in 2011 and currently employs about 350 specialist engineers. In addition to providing an expert advice for the design of Futura Bridge, we also have the capability to build a full-scale prototype. Next slide, please. As mentioned earlier, the bridge is to be delivered on site in 7 parts which will be connected with stainless steel joints. Each part will be made by infusing dry fibers with resin. The build philosophy also aims at developing a tool-free manufacturing method, thereby reducing the need for making high-cost one-off molds. Next slide. While we're halfway through the structural design, we're also considering the design for manufacture. NCC has significant experience with large-scale resin infusion. However, to best understand the specific challenges of building a complex structure like Futura Bridge, it has been considered essential to do a mock-up trial by fabricating a full-scale part of the bridge, which as indicated has been taken at one of the most curved locations of the span. The part is approximately 2 by 2 meters in plan and includes steel plates integrated in the FRP ribs in the transverse direction so that the bridge can be fixed to a rig for load testing. Next slide, please. On this slide, you can see an exploded view of the deck structure. The transverse ribs of the deck will be cut out from pre-cured laminates and connected to the rest of the structure with so-called boundary angles, numbers 13 and 14, which comprise dry fibers infused together with the outer skins. The longitudinal ribs will be composed of back-to-back channel sections infused directly on the foams, number 10. This would allow to insert and adhesively bond steel plates for the side joints, shown as number 12, between the channel sections. It is important to note, though, that the main purpose of the mock-up trial is to test the manufacturing philosophy, and as such, we shall refine the process for future build stages based on the output learning. Next slide, please. Some of the key areas of learning are around assembly and handling of the subcomponents. We are thus using the mock-up to understand the specific challenges about tolerancing and sub-assembly to identify what low-cost build tooling we can adopt for maximizing quality, safety, and rate of manufacture. Next slide. This slide illustrates the infusion process used for manufacturing the transverse ribs. Dry glass fiber sheets, including the steel insert for the test rig connection, are laid up first. On the top of them, we have peel-ply anti-infusion mesh before sealing all in a vacuum bag and drawing the resin through the fibers. This process produces high-quality products and is particularly efficient for manufacturing large structures. Next slide. A few more photos showing the cured and cut-to-shape transverse rib, as well as the foam cores, which are made of recycled material to improve sustainability and have been precisely machined to include recesses for the boundary angles and the surface ducts. You can also see the installation of the boundary angles, which in this case are pre-wetted to de-risk the infusion, but we're trialing different options. The mock-up itself will be completed in the next 2 weeks. Next slide, please. And to conclude the presentation, I would say that the Futura Bridge is very different from most of the existing footbridges because of its aesthetic and character. The use of FRP materials does not only make possible its construction, but brings many sustainability advantages. Building a full-scale prototype gives us the unique opportunity to test innovative build concepts and to explore other aspects such as maintenance strategies and end-of-life options. As emphasized earlier, the project aims to allow for flexibility of the manufacturing techniques so that the bridge geometry can be easily adapted to different setups. And of course, it can also have applications for non-station bridges. Before I finish, I would like once again to acknowledge the contribution of everyone involved and to point out that this project is only possible because of the opportunity for extensive collaboration. Thank you very much.